In this video, we're going to look at some applications of the derivative to business and economics. In particular, we're going to define the marginal cost, marginal revenue, and marginal profit. So let's say we're manufacturing and selling something. And we'll look at a function that takes as its input the number of objects manufactured and gives as its output the manufacturing cost. We'll call this function C of x. And by definition, C prime of x is the limit as h approaches 0 of C of x plus h minus C of x all divided by h. The marginal cost is based on the intuition that these cost functions are probably, in most situations, increasing pretty slowly if you're bulk manufacturing stuff. Like if you've got a factory, the difference between manufacturing 10,000 ball bearings and 10,001 ball bearings is surely pretty minimal. So we've got our cost function, and presumably, the more objects you're manufacturing, the more it costs. But that increase is presumably pretty small. That gives us the following idea, that the limit as this cost function approaches x is pretty close to the cost function evaluated at x plus 1. I mean, if we let h go to 0, we go along this line, but we're barely changing from here when h equals 1. And that intuition gives us the following, that the derivative evaluated at x is approximately equal to C of x plus 1 minus C of x all divided by h. sorry, H is 1 here. The intuition behind this is that because the cost function is changing slowly, the difference between H being 1 and H approaching 0 is very slight. And of course, dividing by 1 doesn't do anything. So the derivative of the cost function evaluated at x is approximately the cost evaluated at x plus 1 minus the cost evaluated at x. So, definition, the derivative of the cost function is called the marginal cost, and the marginal cost represents the cost to produce 1 more unit if we are already manufacturing X units. And if R of X and P of X are the revenue and profit from, remember, we're not manufacturing these units for our amusement, we're manufacturing them and selling them. And if R of X and P of X are the revenue and profit, R prime of X and P prime of X are the marginal revenue and the marginal profit. Let's look at an example of this. Let me example. Let's say we are manufacturing and selling radiators. Currently, we manufacture and sell 10 radiators per day. The cost to manufacture X radiators is X cubed minus 6X squared plus 15X. And this example was made up, but it is realistic in the sense that cost functions are very frequently cubic polynomials. And the revenue we generate can also be a cubic polynomial. And we won't write the formula for the profit down, except to make the observation that the profit is the revenue minus the cost. So this cubic polynomial minus this cubic polynomial. If we increase production to 11 radiators, what will happen to the cost, the revenue, and the profit? This is precisely what marginal analysis exists to handle. We'll take the derivative of the cost function, 3x squared minus 12x plus 15. And we'll take the derivative of the revenue function, 3x squared minus 6x plus 12. We'll look at profit in a moment. But to see how the cost is going to change when we go from 10 to 11 radiators, we'll plug 10 into the marginal cost. And that works out to be 195. So the manufacturing cost is going to increase by $195. Is this increase in production a good idea? To know that, we'll look at the marginal revenue. And it works out, if we plug 10 into this, to be $252. So at least if we neglect any other factors except for cost and revenue, this increase in production is a good idea. The cost will go up by about $195, but the revenue will go up by more than that. So we're making money. How much money are we making in particular? That's the marginal profit. And we can use the difference rule here. The profit is one function minus another. So its derivative is the derivative of the first minus the derivative of the second. We anticipate making a profit of $57 if we up our manufacturing by 1.